Thanks, Carter. So, I'm Ren, and I'm going to be talking about natural language search with OpenSearch today. I'm also going to be talking a little bit about those small models because cool part about my demo is I have turned Wi-Fi off of my laptop. I'm going to be running it completely, including the large language model, on my computer. So this is going to be fun. So diving in, um, we're going to talk about OpenSearch, and OpenSearch in particular is a uh, fork of the Elasticsearch line of products. So this was done by AWS a few years back, and it is a open core community first ecosystem around how do you do not only search and vector search and all of those great things that we need to do in the search ecosystem, but also provide rich dashboarding and things like that that are critical to being able to use this for other applications in your use case. So diving in, we're going to talk about keyword search, everybody's favorite tool of the early 2000s and 1990s. But keyword search is still an important part of any kind of search algorithm that we do today. And there's a traditional algorithm for this known as TF-IDF, or term frequency inverse document frequency. And it attempts to match documents based on keywords and the frequency of those keywords across the entire document set. So here's a quick example on the right-hand side. This is a set of words taken from Shakespeare's plays. And in particular, Romeo is a word only used in one of Shakespeare's plays. We see it in Romeo and Juliet, and we don't see it in the others. Whereas good and sweet appear in all 37 of those plays. So in terms of term frequency, we might see those words good and sweet used a lot in one of those plays, which might give us a higher term frequency score. But more importantly, since they're in everything, we're going to rank that a little lower because it's less unique across all of those different documents, all those different plays. And OpenSearch in particular uses a variant of TF-IDF called BM25. It's named after the Okapi information retrieval system from London. It's a best matching algorithm that kind of does the same sort of thing, but it's just a different weighting system. But it treats each document as a bag of words. So we're not preserving the context within those. We're not preserving the sentence structure. We just know, hey, this is all of the words that are present in this document, and we're going to match the keywords on those things effectively. But for some use cases, keywords aren't enough. So how can we go ahead and look at the meaning behind these things instead of just the text surface forms and how they appear? So this is where we enter the world of semantic search. We have data that's coming in, whether that is text or pictures or audio or video or whatever you have. And then we have embedding models that we'll talk about more in a moment that are specialized ways to take that data that you have coming in and turn it into a vector representation. Now, that's kind of a weird word. So let's talk about vector representations for a moment. So when we talk about a vector representation, it is a mathematical representation of the semantic representation of the text document or whatever else you have. So we start with tokens, right? We go ahead and in both approaches, whether it is keyword-based or vector-based, we break up all of our incoming stuff into tokens. So you can see here, this is a quick sample of breaking up things with a tokenizer. And a tokenizer will chunk up a particular piece of text into words or punctuation or other things like that that may be necessary to understand details of what's going on in it. And with that, you may have noticed using this in pretty much every search application you've ever used, right? When you go to a search bar in Google, it needs to do tokenization in order to break up the words of your query into different ways. And it might be just doing a simple white space splitting on the spaces in between words. And that works really well for English, but tokenization can be more complex for other languages where they don't use white space as a delimiter. But when we go through that, let's make a vector. So when we take a sentence like the cat sat on the mat, right? Just a very simple sentence, we can go ahead and look at co-mentions of words that appear in that appear in that sentence with the word cat. So in this case, we see the word the twice. We see cat 0 times because it's co-mentions. We see sat once, on once, and mat once. So we've made a very simple vector of the cat as it appears in that sentence. And when we do this a lot of times, we have a lot of vectors coming in made from all of the text that goes into training one of these models, we end up with more of an average. Kind of the exact same way that we as humans understand words that we don't know, we look at the context of how it's mentioned. So in this case, I know the cat is some sort of object. I know it can sit, and I know it can fit on a mat. Like those are all things I've learned about this. And that context, as you build it up with more and more data, starts to accumulate a much larger um, corpus and understanding of each of these words. So at its fundamental core, a embedding is a mathematical approximation of the semantic meaning of a chunk. So when we've trained a model, an embedding model, on all of this different data, so much data, that it can go ahead and have not just a first, like one example, but millions, trillions of examples. We can go ahead and combine that all into combining that with attention mechanisms in the LLM to actually understand not only what does this mean, but what parts of those sentences are important. And it learns all of that by throwing more and more data at it generally. So we end up with an average representation that it describes the approximate semantic meaning of that chunk of text that was passed in. And this is where vector databases come in, where we actually go ahead and can represent in vector space the positioning of each of those vectors that came in, and we look for how similar those are to each other. So we might, for instance, pick one and say, okay, here are its two closest neighbors. Now I know how to do that. We do the same thing when we run a vector query, a semantic query. We embed it, we turn it into a vector, and we compare it against all of the existing ones to find its closest matches. And with that, we now have a set of documents coming back that are really helpful to us. But scaling this is always an interesting challenge, right? Because models get larger and embeddings get bigger. So the default embedding size from OpenAI, for instance, is over 1,500 dimensions. So in very large data sets, we have to think about how we maintain the search performance on those vectors. It requires a lot of detailed calculations. It requires some approximations. Sometimes you have to trade off accuracy versus size on disk or in memory. And we think that one of the most interesting ways of doing that is actually JVector. And JVector is a plugin that was written by the DataStax team, a open source library written by the DataStax team, and it is a plugin that uses it for OpenSearch. So this plugs into the Lucene core of OpenSearch, and it provides a much more efficient way of doing large-scale vector ingestion and retrieval. So with this, it has inline vectors stored in the graph, so it can find those very quickly. It can kind of compress those vectors using selective quantization. And it can also, across multiple nodes in the cluster, it can do concurrent graph construction to make sure that it can go ahead and combine those together into an effective queryable graph in real time. Now, I'm going to dive into a demo. And as I mentioned, this is running locally on my machine. So you will see, first of all, that my Wi-Fi is off. And I am using Ollama, right? And I'm using the Granite series of small language models from IBM. And I love Granite, right? It's a really cool set of models using a hybrid Mamba architecture that goes ahead and is a mixture of experts model. Hello, Granite. And it's running locally on my machine. So it'll take a second to boot up just because there we go. But anyway, so it knows that it is capable of doing some stuff. But you can see here that it doesn't know much about its world or its ecosystem, right? It knows that it's an AI language model. It's not a physical object or material. That's where RAG comes in. RAG is all about grounding these large language models in responses that make sense, that use real world data to make sure that those are efficient and accurate to what we're trying to do. So I'm going to go over to this little app I made last night, which is just a basic query interface. So I'm using for this, just as we saw in previous demos, I'm using Dockling, and I'm using OpenSearch, and I'm using the OpenRAG pipeline for ingesting things into this. And then I can go ahead and customize some of that behavior. So for instance, if I ask what is dockling, it'll take a couple of minutes because I am running this locally on my computer. But the cool thing about this is I've gone ahead and made some tweaks to how it does retrieval. And I can do that because I'm able to access the underlying components that make up OpenRAG, which is really, really cool. It opens up the power of doing all of these things and giving me flexibility in terms of what things do I actually want to surface to my application. So here we can go ahead and see it's come back with an answer and says, what is dockling? And talks about how dockling works in OpenRAG. But the interesting part here is actually these right here that I've added, where it knows not only what document did those come from, but the line numbers it came from. And we can scroll down and we actually see all of the source documents coming back from OpenSearch here with scores and different details of what it found in those, which allows us to do rich analysis and kind of make it more grounded for the user, right? Make sure that they feel like, okay, I can trust this. I understand how this is working. I can see the data that it used to construct this question. So just very basic, but I was able to construct that in an hour, right, with the help of OpenRAG, and that's really, really cool. So diving back into the PowerPoint here, I want to show a couple more tips and tricks for this because I am a big fan of not just staying with what you can do out of the box. I want to expand this. I want to do cool things that don't come standard in every RAG application, because I view RAG as like part of a larger system or larger application, right? It's something where you can come in and you can use it to expand out existing workflows. You can use it to ground techniques in when you're doing agentic workflows and combine that all together to make really rich use cases. So let's talk about filters first, where a filter is OpenSearch's way of going through and saying, hey, I don't want to look at all of the documents in here. I want to just look at a subset. So here's just a very basic query filter that will do, hey, I'm looking for only smartphones from brand A. Don't look at anything else when you do your query. And the cool part about this is these are combinable with pretty much everything else in OpenSearch. You can combine them with queries that do keyword searches. You can combine them with vector queries to limit the scope of what it's doing there. And you can combine them with aggregations. And aggregations are cool. Aggregations are the thing in OpenSearch that when you don't want to get documents back, but instead care more about getting an answer back, that is what an aggregation is useful for. So in this case, I want to know what the average price of all the products on my site are with tax. And it'll go through and analyze. In this case, it ran through over 4,000 different products on my site. And it said, okay, the average value here is about $75. And that's really good for me to know, because you can kind of keep an eye on that, and you can do it when you combine it with filters and you combine it with other aggregations. You can look at that over time. You can look at how that changes with different products and different dimensions, and you can use this to build really rich UIs for any sort of search use case. But let's get a little fancier. So this is probably difficult to see at the Zoom level, but this is also available in the OpenSearch documentation. But this is a combination of two queries. It is a filter query that is bucketing an aggregation. So it's saying, okay, I want all of the responses that were successful, a 200 success code, and all of the OS X operating systems to be two different buckets here. And then for each of those buckets, I want to know the value of how large the response was and average that, right? So you can go ahead and start doing multiple levels of this aggregation and see how they compound on each other. And you can combine it with filters. You can combine it with other things in order to get really rich responses back from your data. So one of the coolest things about OpenSearch is not just that it can do document search, it's that it can do metadata search. Right? It can go ahead and combine all of these things around vector retrieval with rich metadata that it can store in its document storage mechanisms in order to be able to filter on all of that at once. And it's really fun. I want to talk about one more thing, because this is kind of my favorite secret feature of OpenSearch, and it's the percolator. So you probably haven't heard of the percolator pattern before, because it's kind of a weird one. But this is an incredibly useful tool for building out rich rich applications that may have a different kind of interaction paradigm than what you're used to. So a percolator doesn't index documents directly. Instead, it indexes queries, where you go ahead and say, hey, here are areas of interest that I care about. And now I'm going to run documents against it. And if any of those match, go ahead and flag it for me. So this can easily turn into a proactive application, which is really cool for agentics, where you can go ahead and say, hey, not only do I want to be able to do this as a user-initiated pattern, I want to start being able to pull in information and proactively tell my user about the things that need to come up in it. So really cool, really exciting. OpenSearch is a great open source project. Really excited about the data stacks, JVector being included in it, and I can't wait to see what you build.